You've reached the last chapter in your ME 2134 thermodynamics class. And the nature of this chapter is give you some introductory ideas about combustion. And why are we interested in giving you an introductory idea on some basic combustion calculations? Think back about your, let's see, that would be chapter 8, I believe, the steam power plant cycles. You needed a high temperature heat source, didn't you? Chapter 10, air standard cycles, all types of different engines, internal combustion engines, the Brayton cycle, in other words, the model for the gas turbine engine. You needed a high temperature heat source with a lot of heat transfer going in to make those systems operating in a cycle operate. And so that's why we're giving you a little introduction to combustion so that you, as a mechanical engineer, have an idea of how would I achieve that Q dot H at some temperature T sub H. And so in this chapter, we're going to give you an introduction, quickly cover the stoichiometric equation for combustion. Gosh, I hope you remember that from either high school chemistry or freshman chemistry. You've observed combustion throughout your lives, right? And so we're going to give you review the basics of burning fuels with a little excess air to make combustion complete. Going to give you the ability, using the first law, to determine how much heat can I get for a certain proposed fuel and air burning situation. Going to give you the ability to estimate the temperature at which the flame operates. In other words, T sub H, going to give you an ability to estimate that. And then finally, some very valuable tabular ability to look up heating value of fuels. So when I was thinking about preparing this, where might I start? And I tried to think back about my own high school experience. And even when I was in high school, we were putting astronauts into space with rockets. And I thought I'd bring this up to current day SpaceX. There's a nice image of a couple of SpaceX rocket engines that you've seen, you're familiar with. And then think about what was I taught when I was learning about rocket engines. So that big, tall, cylindrical rocket is full of basically two storage vessels. One vessel has liquid hydrogen, that would be liquid H2, and a vessel full of liquid oxygen, O2. And when at liftoff time, we start combining the liquid hydrogen and oxygen, it's lit off in this rocket engine exhaust that you see here. A huge amount of heat is released. And what's the exhaust? What's the chemical reaction exhaust? Think about it a little bit. Well, since you're only burning hydrogen, H2, with oxygen, O2, the exhaust is simply going to be H2O. So amazingly, for these rocket engines that you observe on TV, or hopefully perhaps even live, the exhaust is H2O vapor. It's kind of like the simplest example of combustion. And so here, let's think about your high school experience, perhaps your college chemistry experience. How would you set up the combustion equation for this rocket engine? So you start with H2 and O2, but you're not given this reaction formula, are you? You have to sort of figure out, how can I balance the moles of hydrogen and oxygen to get exactly the right amount of moles of H2O? And so you study this equation and you say, oh, I guess I'll have to start with the O. And I see I've got an O over here. I've got an O2 over here. So I'm going to have to put a 2 there to get my O's to balance. Okay, so now if I look at my hydrogen over here on the products, I've got 2 times 2. I've got 4 hydrogens. So back over here, I'm going to have to put a 2 over here to get two H2s. Everything balances, and you feel pretty good about yourself that you've created your own chemical reaction equation for a rocket engine without being provided to you. This is not something you need to memorize. You don't need to memorize this formula. You should be able to get it on your own. And so here we've got liquid hydrogen plus liquid oxygen. On the reactant side, a huge amount of heat is released, and the exhaust is H2O vapor. So I hope that gets you an idea of where we're headed in this last chapter 13. But we're going to be looking at hydrocarbon fuels, not rocket science. And so let's look at one of the most common hydrocarbon fuels, which basically we model natural gas that comes up out of the earth. We model natural gas that we sell commercially as CH4. I hope you did this in high school. I hope you had some exposure to taking CH4, that's your fuel, and burning it with oxygen, pure oxygen, which exists as O2, right? And so you would, again, go through that drill of, now, how do I balance my reaction equation? I think about, now, what are, for hydrocarbon fuels, C sub M, in this case, M is 1, H4, N would be 4. For any hydrocarbon fuel, what are the exhaust products? Your common sense. I hope in high school you got it. Well, one common sense says, I've got CO2. I know that. As a child, I learned that that CO2 is an exhaust product for combustion. But also you do a little thinking and balancing this equation. You say, uh-oh, I'm going to have some H2O as well. And that's something that a lot of folks overlook. So the natural exhaust products of any hydrocarbon fuel are CO2 and H2O. And so instead of dragging you through this balancing, you can probably quickly see that if you do this balancing act on your own, let's say you'd start with the H2O, you figure out you need two H2Os to get your O2s to balance, along with O2 here. Let's see, a carbon, I guess you'd start with the carbon, wouldn't you? You've got one carbon and one CO2 here. So you get the idea that you can scratch your head and figure out this combustion equation, the chemical reaction equation for combustion. Important thing to get in your mind is that remember that the exhaust products for any hydrocarbon fuel is CO2 and H2O in some molar amounts. Okay, so here's the basic idea. Any hydrocarbon fuel. So let's list, what kind of hydrocarbon fuels are there? Off the top of your head, propane gas stoves, natural gas, commonly used for heating, for producing steam in boilers, gasoline, of course, for automobiles, spark ignition engines, diesel fuel for diesel engines, wood, good for burning in the fireplace, good for toasting marshmallows, coal, good for generating large amounts of steam in large boilers, waste paper. In other words, anything that will burn, any hydrocarbon fuel that can burn, you can combine with air, right? So in the real world, except for rockets, we combine our fuels with air, don't we? Not oxygen. We don't have pure sources of oxygen just laying around everywhere, but we got plenty of air existing in our world. So we've got air. It's a natural mixture of nitrogen and oxygen. You covered that in chapter 12. And what are the exhaust products? CO2, H2O, and I've got this nitrogen in the real world. So nitrogen is going to be carried along. It's going to be exhaust products, and there will be some in the real world, other trace products. And recognize that there's a tremendous amount of heat released as a result of this combustion. So that brings us to the end of our intro. And so just sort of quickly browse these images that I've decided to share with you. You've observed combustion reactions throughout your entire life. And you've got some experience with balancing simple chemical reaction equations in high school and college chemistry. And so I'm going to suggest that you're pretty well set up to do well in this chapter, as long as you couple that and recognize what we've got coming is we're going to use that first law of thermodynamics to figure out how much heat will be released for our proposed hydrocarbon combustion process. I've got another few modules to cover piece by piece to review with you the stoichiometric equation, getting a little more advanced and burning hydrocarbon fuel with stoichiometric air, then excess air, and then figuring out the amount of heat released. So I hope this helps, and hang in with the next few modules to give you some tips on how to do well as you finish up this course in thermodynamics.